Hi, folks. We're on day 11 now, which is the second day of error correcting codes. We're also going to talk a little bit about Shannon Theory one more time. Let's go ahead and get started. So, we've looked at the Hamming code already. The Hadamard code, which is, depending on who you look at, sometimes it's also called the Walsh-Hadamard code. Hadamard died before coming up with an application for his theory, and Walsh was the guy who sort of, married the theory with the application. That's the idea here. But we'll just keep the name simple. We'll call it the Hadamard code. It's a code that can correct multiple errors. And this makes it suitable for noisy transmission channels. When we talk about the Hadamard 32,6 code, greatly increases the data size. We're only taking 6 bits of input and generating 32 bits of output, but it can correct up to 7 errors per block. Up to 7 out of 32 errors can be corrected out of this. So here's the sort of the background. Jacques Hadamard was a French Jew. He had built the ideas behind this code when he was a young man, but he was forced to flee Europe during World War II. And in the process of fleeing Europe, he had to leave the university position that he had, and sort of was not able to sort of finish his research and get it published. And so Joseph Walsh was an American mathematician who met him after he had fled and sort of picked up his work and applied his matrix theory to digital communications. And so this was a collaborative process, but Hadamard probably would have been able to finish the work himself had he not been, forced to flee. The 32.6 code was used to transmit photographs of Mars back to Earth from the Mariner 9 probe. The probe transmitted grayscale images using 64 shades of gray per pixel, and 64 is 2 to the 6th power. And so each block in the Hadamard code represented the color of 1 pixel. We're taking 6 bits of input. This is the color of 1 pixel. And we're putting enough error correction on it that we can correct 7 bits out of the 32 bits that are transmitted. And so that we want to be enough to be able to overcome the error rate in transmitting all the way back from Mars. That's the idea. So here's the way the encoding works. What we're going to do is we're going to take a 6-bit data block, and we're going to encode it with a 32 by 5 matrix. I can't fit that entire matrix because it's got 32 rows in this slide format, so I'm going to attach it to a separate handout. But I've also got it on an upcoming screen, but it's very tiny here. But this is an easy matrix to reconstruct. The rows are just the values in binary of the numbers from 0 to 31. And so here's how we're going to encode a 6-bit block. What we're going to do is we're going to label the bits 0, 1, 2, 3, 4, and 5. So x0, x1, x2, x3, x4, x5. We're going to form a column vector that only contains x1 through x5. x0 is not part of this vector. All right. We're going to multiply this vector by this matrix G, and I'll show you this matrix on the next page. But here's what the matrix looks like. The top row is all zeros. The next row is the binary representation of the number 1. The next row is the binary representation of the number 2. Then the number 3. Then the number 4. All the way down until we get to the binary representation of the number 31. That would be 30 rows, 32 rows by 5 columns. We're going to multiply, that's a 32 by 5 matrix. This is a 5 by 1 matrix. We're going to get a 32 by 1 vector. And then we're going to calculate, because this is in binary, this is going to be either, basically ones or zeros. And then we're going to replace every entry in this vector that we get with, instead of zeros and ones, we're going to encode it with negative ones and positive ones. So negative 1 to an even power is a 1, negative 1 to an odd power is a negative 1. And then, if this bit is on, if that's a bit's a 1, then we transmit the negative of that vector, so all the negative and positive signs flip. And if it's a 0, we transmit the positive of that vector. So that's going to be the idea, that this bit will then govern whether we transmit the vector we've calculated or the negative of the vector we've calculated. So this sounds complicated, but it's not. Let's go ahead and walk through an example. So we want to encode this string, 011101. So what we're going to do is we're going to strip off the leftmost bit. This is my x0. And we're just going to encode the matrix 11101 into a vector. And then we're going to multiply that by this encoding matrix G. All right, we're going to get a vector W, which I'm going to show you on the next slide, but again, it's tiny. But it's too tall to fit in this slide format. All right, so let me show you what's happening there. I'm going to stop here and come back to this moment later on. So this over here is my matrix G. This is the vector that we're encoding. And when we multiply G times V, what we end up getting is, actually, further down we start getting numbers like 2, 3, and 4. The bottom row, for example, 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 0 plus 1 times 1. This would have been a 4, but I'm just recording the answers mod 2 because I really just need to know whether this number is even or odd. And so the formula that I'm using up here is I'm multiplying the two matrices, and then I'm taking the result mod 2. All right, so what we're going to do in the next process is then convert this 0 to a 1 and this 1 to a negative 1. This 0 becomes a 1, negative 1, and so on and so forth. And because the original bit that we didn't encode here is a 0, we'll transmit this vector as is. If this was a 1, we would transmit the negation of this vector. That's what we're going to send. Okay? All right. So let's come back here. So we compute W star by replacing each entry in the vector by negative 1 to that power. That's what we did by hand. And since the leftmost bit in the block was a 0, we'll transmit that vector and we're not going to negate it. Okay? So that's all we're doing, is we are taking the last 5 bits of our string, multiplying it by this matrix that records separately the product of this vector with every binary number from 0 to 31, records what those are in binary. These are just like checksums against every possible binary number from 0 to 31. And then, depending on what this bit up here is, we would either keep the signs or change the signs. So then when we decode this message, we take the message that we've received, and we're going to multiply this matrix by a big 32 by 32 check matrix. I'll show that to you in a moment. Any two columns of that vector's matrix C have exactly 16 entries in column and 16 entries that are different. And that's the key to the error detection, is this C matrix here. We'll show you how that works in a moment. All right. So this is the matrix that we received. This is over here, V. Here's our check matrix, C. And let me see if there's a way that I can do this. I don't want to... There we go. This matrix here has this pattern here. Let's see if I can... well, yeah, I can do that. If I look at the... It's a 32 by 32 matrix, but if I look at this first quadrant, and I call this first quadrant, say, A. Oh, shoot. A. Then I find that the entire quadrant is repeated over here and down here, but this quadrant is exactly negative A. But that pattern reproduces at a smaller level. If I look at this 8 by 8 matrix, and call this matrix B, then this quadrant is B, this quadrant is B, and this quadrant is negative B. And then if I went up to this 4 by 4 level, and call that matrix C, then I would have C and C and C and negative C. All the way up to, well, all the way up to 1 by 1. That this matrix is sort of self-replicating at higher and higher levels as we go out. And so this matrix has some peculiar properties, but what happens is when I multiply this matrix by this vector V, what ends up happening is that I get a column, where'd my pen go? There we go, of all zeros except for this one entry at the bottom. This is 32, and that's the problem. I need to bring it back into black. There we go. Now I can see the pen. And the position of this 32 is in the row that corresponds to the binary representation of the message itself. Remember that the top row, when we encoded, was the row 0, row 1, row 2. This was row 31, 30, and 29. And so what's happening is this row is being identified because it's the only non-zero value we've got here. And it's in row 29. But 29 in binary is 11101. But 11101 is exactly the vector that we were encoding up here to begin with, 11101. And so the row number turns out to match with the message that we were sending. So that's what happens. We have this complicated matrix of zeros and ones. We multiply it by this vector V that we have transmitted. If everything worked out nicely, we get a column of all zeros except for one entry. And that one entry will be in a row. And if we write out that row number in binary, starting with row 0, ending at row 31, that row will be the message that we want to encode. Okay? But that's if the message was transmitted without error. W will consist of all zeros except for one entry, which is either a 32 or a negative 32. If we get a 32, then the position of that entry corresponds to the column of C that contains the encoded message. So that's what we meant. If the entry is a negative 32, then that negative sign indicates that we have to, instead of prepending a 0 in front of there, we want to prepend a 1 up there. That Not a -1, just a 1. Fix that. That a -32 means that there has been a sign change, and that sign change was what that 1 indicated. So that's what happens. If everything works out without error, that's the important thing, we get a column of all zeros except for either a 32 or a -32. Okay? So what happens if there is a single error present? Okay? So let's go back over here. If there was a single error present in this V, then one of these rows would change by a factor of... In fact, some of these rows will change by a factor of +2, and then this row will change by a factor of -2. And so this would be a 30 instead of a 32. And so we could still read the message correctly even though that there was an error. If there was a second error, then some more of these rows would go up by 2. And in fact, one of these rows that was already 2 might even go up to a 4. It affects these wrong rows by up to a factor of 4 now. And then it would affect this correct row by a factor of 4. And so it might be a 28. But 28 still is much bigger than 4. Let me show you what's happening here. If there are no errors, all of the wrong rows will be 0, and the right row will be either a 32 or a -32. If there's one error, then the wrong rows can go anywhere from -2 to +2, so that the wrong rows have increased their range from having to be 0 to being maybe off by a factor of 2. And then the right row could also be off by a factor of 2. If there are 2 errors, the wrong rows will be off by a factor of 4, and the right row could be off by a factor of 4. And that keeps happening as the number of errors increases. Even if we have 7 errors, the wrong row will be in the range from -14 to 14, but the right row will be in the range from 18 to 32, or from -18 to -32. And so I'll still be able to tell the correct answer, even though there are 7 errors. Once we hit 8 errors, that's where we start to get muddy. The wrong rows can just show a range from -16 to 16, and the right row might also show a 16. And that's where things start to overlap. On the 8th error, the ranges overlap. A 16 can show up in the wrong row or the right row, and that means that we cannot unambiguously decode 8 errors, but the correct row will be one of the rows with a ±16 in it. And so the decoder may only have to consider a few cases instead of all 32. And so the Hadamard code absolutely will decode up to 7 errors. And then with an 8th error, it's still better than brute force. There is some error recognition present at the 8th error that the correct row will be one of the ±16s in this case, and there may not be more than a handful of those. And so we have at least sort of enough information to maybe make an educated guess at that point. So Hadamard code degrades a little gracefully on the 8th error. By the 9th error, we're not getting much information at all, though. Okay? So once we have identified the correct row, this is a sort of a complicated process for extracting the original 6-bit message. That I think it's easier to extract just the row number. I'm going to go back to here and erase some of the chicken scratch that I had up here from earlier. I think it's easier just to say that this being a correct row is row number 29, and 29 in binary is 11101. The other way that we can do this is to look at this row here and look at the powers of 2. So 1 is a power of 2. The second column, 2 is a power of 2. Let me think about this here. Except that we're starting with 0. 0 is not a power of 2. So 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Starting with the 16, remembering that -1 came from an odd number and +1 came from 0, even power. This is odd, 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 even, and odd, which is 1, 1, 1, 0, and 1. The powers of 2 columns in this row, if you read them from right to left, will give you back the representation that we wanted. Again, this first column is column 0, and in fact, column 0 only contains 1s. It never gives us any useful information. So that's the idea, is you can read the bit string instead of taking the row number and converting it to binary by actually just taking the power of 2 columns and arranging them from highest to lowest and converting those into 0s and 1s. And that's the process that they've described on this slide here. The bits located in the 16th, 18th, 4th, 2nd, and 1st, where we start numbering with 0. Okay? That's just an alternate way of reading what that message is. Okay? All right. So let's move on and talk about Shannon Theory for a second. We have talked about Shannon's paper a little bit. This is the paper that was written first but declassified second. And so this paper was delayed because there was some classified material in the paper, and it took a little bit longer to release it. He proves the theorem in the book. We've talked about this theorem before, that any crypto system, in order to achieve perfect secrecy, has to have a random key, and the random key has to be as long as the plain text itself. That's sort of significant. That is, if Alice and Bob need to send a, say, 1,000 character message, and they want perfect secrecy, they need a 1,000 character key, and it has to be completely random. And if they have some way of communicating that key to each other that's secure, they may as well just communicate the message over that channel. That is, communicating a key that is the same length as the message is sort of problematic. The idea is that you want to be able to communicate a key quickly and secretly, and then use that key to encode much longer messages. And so perfect secrecy in theory is possible, in practice it's very hard to implement. And so he talks about 2 ways that we can approximate perfect secrecy. How can we maximize secrecy with a smaller key? These do not, because of this theorem, it doesn't actually achieve perfect secrecy, but they are the 2 ways that we can make this crypto system harder to break. And he calls these methods confusion and diffusion. Okay? And the goal of these methods is that if somebody has access to the ciphertext, like Oscar, who can read the ciphertext, that the ciphertext should not reveal any redundancy or patterns that the plaintext reveals. All right? So confusion is the idea that the relationship between the ciphertext and the key should be complicated. And here's an example. In a Visionaire cipher, if I have a message, so this is my message, and this is my key. So word. The relation between the ciphertext and the key is pretty straightforward, that the W encodes this character, and the O encodes this character, and the R encodes this character, and the D encodes this character. And so this is what makes the consistency test possible, is that there's a repeating pattern of the characters that are encoded with a W, and repeated characters that are encoded with an O, and repeated characters that are encoded with an R. If we want to confuse this, we might want to do something where we rearrange the key each time. So as a modified Visionaire, so we still have a message. This is my message, but so let's think about doing something with the key so that we're not having the W's occurring in repeated places. So for example, we might take the word the first time and repeat the W at the end. Then repeat the word, but this time, instead of repeating one letter from the word, we'll repeat two letters from the word. W-O. Then we'll repeat the word, and then the next time repeat three letters from the word. So the whole word plus one letter, the whole word plus two letters, the whole word plus three letters. That would make the pattern a little bit, it would interrupt the pattern, so it wouldn't be every four letters now. It'd be like the W got used at positions 1, and then 5, and then 6, and then 7, 8, 9, then 10, then 12. And you can see that already that pattern just becomes a little bit harder because we're using the key in a less repetitive way. And so the idea is that the relationship between the ciphertext and the key should be complicated. What we're going to do with the key is we have to use it in a way that is not cyclical or repetitive, so that we have to do something funky with the key so that it doesn't reveal a pattern. And then diffusion. Let me get to talk about confusion again for a moment, and then we'll get to diffusion. So substitution cipher does no confusion at all. We are just changing one letter to other letters. The frequency and letter patterns in the plain text are identical in the ciphertext. We're just changing which symbol we're using. Visionaire does a higher level of confusion, but again, like we just saw in the previous example, it's not perfect. The Enigma Machine, which we are going to look at very soon, I keep talking about it, and we really are going to get to it soon, does a very high level of confusion by using a series of rotors to change the substitution cipher for every single letter. It's not quite random, but the rotors are arranged so that it takes over 17,000 characters of plain text before they start to repeat. And so it's like a substitution cipher with a very, very, very long period. And since most messages are, if they could keep the messages short, we won't hit that 17,000 character limit. So then diffusion is based on the idea that patterns that are in the original text can be hidden by spreading out that location. Y'all did an example of this on homework 1, where we can hide the pattern QU by rearranging this in such a way that the Q and the U are not side by side anymore. That splitting this up into blocks and then rearranging those blocks made this pattern not side by side anymore, and this turned out to be a challenging problem to break for some people. Just by diffusing the repeated pattern here, or not the repeated pattern, but the obvious pattern QU. So that we are taking a pattern that is inherent in the regular text, we're splitting it up so that the Q and the U are now in different places. In a crypto system with a high level of diffusion, if we change a character in the plain text, we might alter several characters of ciphertext. That is, so if I want to change this message from Mary to Gary, I don't know why I would use Gary, but that instead of just changing one letter into plain text, this change diffuses and causes several characters in the plain text, in the ciphertext to change. And so that message gets scattered throughout, that alteration scatters through multiple locations. And AES, which is the capstone project for the course, will achieve diffusion in a pretty high level because it does this operation where altering a single bit of the plain text is going to alter multiple bits in the ciphertext. And we'll see how that works later on. Okay? The AES crypto system is an example of a substitution permutation network, which combines a substitution operation, which replaces a block of bits with a different block of bits, and a permutation operation, which takes bits and then rearranges them. That's how we're going to achieve confusion and diffusion. That we're going to, first of all, replace a block of bits with a different block of bits that may not have the same number of zeros and ones. So we might replace the block of bits 0010, which is 3 zeros and 1, with a block 1010, which is 2 zeros and 2 ones. And so now there's the pattern of how many zeros and how many ones is no longer preserved. And then does some rearrangement operation so that we can't necessarily predict where those 2 zeros and where those 2 ones are going to end up being. That's the idea. AES is a challenging substitution permutation network that we're working on, large numbers of bits at a time. But what we'll do over the course of the next few days is we're going to look at the Enigma Machine for a couple of days. We're going to look at a sort of a baby version of the substitution permutation network first, like a simple example, just to get an idea of how all these operations tie together. And then we're going to start looking at AES. And so we're going to get through those 3 crypto systems in the next couple of weeks. Okay? Well, thanks for putting up with me. I'll see you guys on Wednesday.